Good morning after a long gap. So while it feels like a long gap to me, but you've still been having your classes, though I think there were not many classes, right? You had quite a few holidays in between. So we get back to light, to optical engineering, and we start a new topic today. We're going to look at interference. And since this is a course on optical engineering, we're not going to spend too much time on interference itself, but we kind of almost immediately go into the application of interference, which is interferometry. Okay, so I have some pictures up here, some beautiful pictures up here, right? One is of some oil spill on the road, you see that quite commonly, and the other is of a soap bubble. You see these kinds of images, I'm sure you can tell me hundreds of other examples where you have noticed or seen such images, I hope, because if you haven't, that means you're not being very observant at all. And why do we see these? What is the reason that you see these nice patterns and you see these variations in color? Well, really, it is because of the phenomenon of interference. You cannot explain these images if you stick to your ray optics picture of light, your geometric optics picture of light. These are only explained when you go to the wave phenomenon. Okay? So, as I said, in this course, our goal is to get you up to speed as quickly as possible in the application part. So, I'll do a very quick introduction to interference, and then we'll start looking at how and why it's useful, where you can use it. Okay, so in order to see interference, some conditions have to be met. We do see these patterns often, but you don't see these patterns always. So some conditions have to be met, and one important condition that has to be met is that the light that is interfering has to be coherent. Okay, so coherence, you are not going to see interference if you do not have coherence. Okay, so what do we mean by coherence? Right? Now, if you think about it, the pattern you saw is showing you where one beam, let's take a simple case where you have two beams of light and we say they're interfering. You get this kind of fringe pattern, even what I showed on the previous slide. We see some regions of, in the previous slide, maybe I can just go back. If you see this image over here, you have one region which is all blue, another region which is all magenta, another region which is all one particular color. That means some condition is satisfied in that region for that wavelength. And that's why that wavelength has become visible to us. Okay? And that condition is not satisfied for the other wavelengths in that region. So you can think of this interference pattern like a map, right? You have these maps which show you regions that connect points of same pressure or same, you have an isotherm, points of same temperature. Well, the interference pattern is nothing but a map of that nature. What is it connecting? Points of same what, do you know? Can you think of? So what isotherm is a graph that shows you the points of the same temperature. Right? So no, it is not same wavelength, it is same phase, right? In other words, same optical path length, right? So wherever, and we'll see these conditions, but if you think of the interference pattern as nothing but an iso-optical path length, it's connecting regions of the same path length. And wherever there is the same path length, where is that going to happen if you assume that this film has thickness of same, so let's say you have some film of some varying thickness. And let's say it's uniform refractive index, so it has the same refractive index throughout, let's say. Whenever the path length difference matches some condition for one wavelength, that wavelength is going to be predominant. Okay? And this will get clearer as we go along. But think of the interference pattern as nothing but connecting points, a graph that connects the points with the same optical path length or the same phase. Okay? Okay. So, in order now, so now I have connected interference to phase, but if I want them to have the same phase, if I want to see an interference pattern, that phase relationship between the beams that are interfering, that must have some stability to it. So, think about phase itself just from the point of view, forget interference, just think about phase itself. If I say a wave has a particular phase behavior or a phase structure to it, we are able to write out an expression for a wave. So, if you look at the expression for a wave, we can say it has a certain amplitude and then it has exponential j omega t minus kz, let's say, right? Oh, sorry, I don't write the j over there. So, it is exponential omega t when that's right. Okay. So, what do we mean here? I have a certain phase. This allows me to predict how the wave is going to behave. So, I know what the phase of the wave is, what the amplitude of the wave is at some position z, at some point in time t. This relationship, if the wave obeys this relationship, it means I can predict what is the expression for the wave after some time z, after some time t at some other location z, right? The fact that I can write out an expression like this, and this expression will hold true for all time t and for all z, means my wave is behaving in a consistent way. And really, coherence is talking about how consistent. We blindly write out this mathematical expression and we've always written it down. But you could actually ask, when I write out this expression for a wave, does this mean for all time, whether I put t equal to 3 picosecond or t equal to 10 to the power 12 seconds or hours or minutes, will this expression hold true always? And it turns out it may not. Now, the expression may hold true, but these relationships omega and k, or sorry, these terms omega and k, they don't actually stay constant. Okay? So, coherence is the way to study what is the stability of this wave. With what accuracy can I predict something about the wave if I know everything about the wave at some time t and at some position z. So, you say it's coherent when you have a fixed phase relationship between the electric field at some position at some time and the electric field at another position at another time. Okay? If you have such a wave, we call it coherent. Now, no wave will have a fixed relationship for infinite time and infinitely positioned locations. So, the degree of coherence depends on how far you can go away and still say the wave at this far distance or the wave that is much delayed is still correlated to the wave I am measuring at this place at this time. Okay? If the correlation is lost very quickly, we will say that this light has poor coherence. If the correlation lasts for a long time over long distance, then we say that this has a strong coherence. So, you can have a degree of coherence. Now, it should be clear, or maybe it's not that clear, but if I take a source like a white light source, say from a tube light, and I take a laser, and if I were to compare the coherence of these two sources, they don't have the same degree of coherence. So, if I want to do an interference experiment, can I do it with a white light source, with a tube light? Do you think? someone says yes and they're right, you can, there is coherence. Can you do it as easily as you would do it with the laser? The answer is no, because a laser has a very high degree of coherence. A white light source has a very low degree of coherence. So setting up an experiment with the laser is easier than setting it up with the white light source, but it's not impossible. Okay, and we'll see what would be the differences between these two sources and why sometimes. So you might say, oh, so we'll never do interference with a white light source. Sometimes you choose a white light source because the ease with which you get fringes with a highly coherent source can sometimes be a problem for you. You don't want to have so much information and you're getting information. So sometimes a white light source is chosen. You have specific systems where the source has poorer coherence on purpose. Okay? So this is an image of, by now you should know, this is how a Gaussian beam, the wavefronts of a Gaussian beam as it's propagating and as it's propagating through its waist. Okay? So you have the plane wave nature in the middle and then as it propagates outward from that. Okay? This is how a beam would look if it had perfect spatial and temporal coherence. But let's say that the beam had very good spatial coherence and poor temporal coherence. So what does that mean? So we can talk about coherence as being the relationship between the phase at some point of time and space with respect to the phase at another point of time and space. In spatial coherence, we're saying just look at the wavefront. What is the relationship at different locations on the wavefront? So it's on the same wavefront, so you're not talking about different instances of time, and that's why we refer to this as spatial coherence. And you can see here that the way this image has been drawn, we have anywhere here the relationship is good. So anywhere on the wavefront the relationship is good. But if I know the phase here or I know the phase here, I cannot definitely predict the phase here because there's a gap over here. Something has happened to disturb the beam. Yes? Oh, sorry. Okay, maybe I use the mouse. Can you see the mouse movement? Right? So basically what I'm saying is if these are your wavefronts, if I know the information here, if I have a source with good spatial coherence, that means I know what it will be here on the same wavefront, right? So I know everywhere, in fact when we define wavefront, we say these are the surfaces of constant phase. So ideally, if I know the phase at some point on the wavefront, I'm saying everywhere on the wavefront that's what the phase will be. But a beam with poor coherence, the phase can actually get slightly altered. You can think of it as it has an aberration. It doesn't have the phase it ought to have. So although I know the phase somewhere here, it ought to have the same phase somewhere else on the wavefront, but because the source has poor spatial coherence, it may not have. Okay? In other words, if it has good spatial coherence, I know that the phase everywhere on this wavefront will have the same value because every wavefront has the same phase. Right? Okay. What is lacking here is temporal coherence. So we are saying this is a source which has high spatial coherence. That means everywhere on a wavefront I can tell what the phase is, but I cannot predict the phase at some later time. And so if you look at the earlier image, this is how I expect my Gaussian beam to look. So if I know the waist is here, then just using my Gaussian beam expressions, I know that if it travels a certain distance z, I can choose what that value of z is. I say this is what the field is now, because I know exactly how the phase has changed. The change is caused only by the optical path length traveled by that beam. But now in this beam with poor spatial coherence, with good spatial coherence and poor temporal coherence, I cannot predict what the wave will look like at some later point of time. You can see something has happened in this region over here, which means this point here does not necessarily have the same phase relationship it ought to have had if this was a perfect beam with perfect coherence. Okay? So, the easiest way to think about it is spatial coherence means you have a source where different points on the wavefront will be well correlated with each other, but not correlated to a point at a later time. As you should imagine, temporal coherence is just the opposite. So, if you move from one point to another point on the wavefront, there is some errors there. But if you move from one point to a later point of time, that relationship holds true as it would for the ideal case. So, you can see here we have tried to depict that here by saying the wavefronts aren't smooth now. It's like there's some error in them. But from one point, let's say I'm from this point and I want to predict what's happening at this point, I will be able to predict accurately. Okay? So, temporal coherence means then you have a strong relationship between electric fields at one point of time and a later point of time or another point of time. Okay? Okay. How do we study these? If I want to look at a source and find out, does this source have good spatial coherence, good temporal coherence, and what in fact affects the spatial and temporal coherence of a source. Now, our ideal sources are always point sources. If you had an ideal source, that means you had a source that was infinitesimal in size, it would then have perfect spatial coherence. Why? Because the source is so small, you consider that only one wave is emitted from that source. Where does the origin of the lack of spatial coherence arise? You think of a source and you say that the source is actually this big. It contains many emitters. So, every emitter is sending out one wavelength of light. And the moment I have a number of wavelengths coming from various emitters, they now are slightly different from each other. Right? So, when can I perfectly predict a wave? If I know everything about a wave at one point of time and one position, when can I always predict where that wave will be or what the amplitude and phase of that wave will be? If I have a sine wave or a cosine wave, right? So, if I say my field is A sine omega t plus kz, this is the ideal case. I can always perfectly predict. You give me the position and time information of this wave, I will then be able to predict what its amplitude is at any time at any position. Right? When you have a source that is not a point source, it means you have a number of emitters and each emitter is emitting a perfect sine wave. But now these different sine waves need not all be in phase to start with. They may be emitting at slightly different times. So, while each of them is a perfect sine wave, the combination of them is not all a bunch of waves in phase. The phase difference may be small, but there is a difference. You have to understand that light is very, very sensitive to small changes in phase. So, sometimes when we do derivations, we say, let's assume there's a change in some parameter and it's a small change and therefore we neglect that change. In the case of light, if you wrote out an expression for the electric field, whether I write A sine omega t or A sine phi or A exponential j phi, if I said I'm making measurements on phase and amplitude, and the accuracy with which I make the measurements is not very good in the amplitude. So maybe I have a plus minus 5% error, even a plus minus 10% error in the amplitude. That might be quite acceptable. But if I say there's an error in phase of 10%, it's totally unacceptable, because the way light, the change in this expression for even a small change in phase is very, very large. Okay. So, changes in phase affect light very strongly. So, if I have a source that is a distributed source, that means it isn't just one emitter emitting one perfect sinusoidal wave, but a number of emitters each emitting one perfect sinusoidal wave. But since they are not all they don't start in phase, there's a phase difference between them, and that is what is going to relate to the overall coherence of your source. So, how do we study the spatial coherence? Well, you might have done these experiments in, I don't know, school or lab, even a physics lab. We want to study spatial coherence. So, we want to study how well correlated is one point of the wavefront with another point on the wavefront. So, you can do a Young's double slit. So, you have your source and you have two slits. Okay. So, now let us say light is being emitted by this source, and the same, so you have the wavefront over here now, right? And from one wavefront you have light coming from this point of the wavefront and from this point of the wavefront, and then this travels, sorry, straight line, and in this region there is an overlap between these two wavefronts. They are both, so you have generated two sources. Those two sources came from the same wavefront from one source. And now the interference you observe in this region can be used to analyze the spatial coherence quality of this source, right? Of course, it depends on various things. It will depend on this distance, it will depend on this gap, it will depend on the width of these slits, depend on the wavelength, and I say lambda, but of course, whenever we say lambda of a source, it does not mean that the source has only one wavelength. Okay. Now, sources that have poor spatial coherence, so with any source, I will say, I may say that the wavelength of the source is 633 nanometers. But associated with that source will be a bandwidth, delta lambda. Now, for a monochromatic source, that means the fact that I call it a monochromatic source means that delta lambda is small. And we'll put some numbers to that as we go along. Okay? So, delta lambda is small for a monochromatic source. In fact, delta lambda for a white light source can stretch anything from 400 to 700 nanometers. So, you can be talking about 300 nanometer delta lambda for a white light source, and that is a source with poor spatial coherence. So, you know now that a monochromatic source, it has to be much less than delta lambda, the spectral width has to be much less than 300 nanometers in order to have good spatial coherence. Okay? How do I study temporal coherence? Well, this particular setup, the Young's double slit, allowed us to make two sources out of the same wavefront. So, somehow I need to now take my original source and create two sources again, but not from the same wavefront, because I don't want to study spatial coherence anymore, but from a wave, two waves, one of which has traveled a longer time or a longer distance therefore than the other one. Okay? So, what is a common, there are multitude of interferometers. An interferometer is a device that generates two or more beams that you will bring together and interfere and thereby extract some information from it. So, the way in which you generate those beams defines what type of interferometer it is. Okay? So, a very common interferometer is the Michelson interferometer, and in the Michelson interferometer again you have a source. So, let us say you have a laser, you have a beam splitter. Okay. So, no guesses, no marks for guessing what it does. Okay. And then you will have a mirror, another mirror, and then, okay, let me remove this. Okay. So, now what happens? Light from the laser hits this beam splitter. You can choose the ratio that you split, but typically let us say 50% of that light goes to this mirror. I haven't drawn this correctly. And the other 50% will go to the other mirror. So, some light has travelled here, it reflects off this mirror, and I have drawn a general case over here, but in particular for the Michelson, you would really want this mirror to be at 90 degrees to the, so that you have normal incidence basically. Okay. So, this configuration allows the light that is incident to hit the mirror. It is at normal incidence, so it travels back. You would again have this mirror. Okay. So that the second beam also hits at normal incidence and it travels back, and both these beams now will come through here. Okay. Now, I drew the mirrors tilted because if you really want to see the fringes, you need to have a slight tilt between the beams. So, I have drawn lines, the red lines indicate the path that light is taking, but actually I might have an expanded beam so that I can see the fringes. Okay. We'll come back to the Michelson interferometer in more detail. What's the point or the difference between the Young's double slit? In the Young's double slit, the slits ensured that you made two sources out of the same wavefront. And then you looked at the interference pattern of the two waves coming from these sources. And therefore, that interference pattern would tell you about the spatial coherence of the source. In the Michelson, the two beams now travel different paths, and I've on purpose drawn one length as much longer. So, let us say this is L1 and this is L2, and I have drawn L1 greater than L2. So, one beam is travelling a greater distance. So, if I look at an interference pattern here, it is as if I am interfering a wave with a wave that has travelled longer and comes a delayed version of that wave, right. So, now when I look at the interference, that interference will tell me how well does it happen, how well does the interference happen for a wave that is delayed. So, I could consider changing the length L1, and maybe initially L1 is equal to L2 and I have a very good interference pattern, then I slightly increase L1 and I still have a good interference pattern. But as I go on increasing L1, I can see the quality of that interference pattern goes on decreasing. And at some point I may not see interference anymore if I go beyond the temporal coherence of that source. Okay? So I hope you can see the difference between these two types of interferometers. One is, both are interferometers, both are creating two sources out of a single source. One allows you to study the spatial coherence, one allows you to study the temporal coherence. Okay? Now, the spatial coherence, I told you, is already related to the size of the source, because I can consider a source that is spread in size having many emitters. But even a source that is small, even that has many emitters, and they are not all emitting at the same time. And therefore, I can relate all the different emitters to the temporal coherence. So we relate the spatial coherence to the size of the source and the spread of the emitters, and we relate the temporal coherence again to the different emitters, but to the fact, to the specific fact that they have a large line width. So typically a source with poor spatial coherence will usually also have poor temporal coherence. Okay? It's quite hard to achieve a source with good spatial and, sorry, what did I say? If you have good spatial coherence, it does not necessarily mean that you will have good temporal coherence. But if you have a source with poor spatial coherence, it's quite impossible to have very good temporal coherence. If you have poor spatial, it's most likely you also have poor temporal coherence, okay? Because you have these number of emitters and they will be out of sync both spatially as well as temporally in most cases, okay? You can have a source with very good spatial coherence, but the temporal coherence may be poor. Okay. So, how do I actually relate these parameters now to and quantify the coherence? So, let us look at the case of the temporal coherence. So, we now know that the frequency of the source nu is equal to c by lambda. Let us assume that light is traveling in free space. Okay? So, the velocity is 3 into 10 power 8 meters per second. Now, let us take a typical lab source. Source is a helium neon laser. Its wavelength is 632.8 nanometers, so it's in the red. And its spectral width, that means the spread. So we say this, we call this a monochromatic source, but it doesn't mean it has just one wavelength. There's always a spread, and the spread here is 2 into 10 power minus 3 nanometers. So if you compare this with the wavelength, well, it seems fairly small, right? The wavelength is 632 nanometers, and this is 10 power minus 3 nanometers. It's orders of magnitude smaller than the wavelength. And that's why we say this is a monochromatic source, because the spread is so small compared to the wavelength. Okay? If I differentiate this expression so that I'm able to relate the spread in frequency to the spread in wavelength, you will get delta nu is equal to c. I'm not worried about the minus sign here because I'm worried about the range of values. Okay, we're not worried about the signs. Delta nu, so this spread delta lambda relates to the spread in frequency by this relationship. So I've done nothing but a derivation of nu is equal to c by lambda. Now for this wavelength with lambda 632 nanometers and delta lambda in the order of 10 power minus 3 nanometers, you can calculate delta nu is 1.5 gigahertz. So what does this delta nu tell us? What do you think it tells us? I've been doing all the talking here. Now you do some talking. What do you think this delta nu tells? Remember, why are we looking at all of this? We're trying to understand temporal coherence, right? And what is coherence? Coherence is the correlation between the electric field. And we are talking about temporal coherence, so we are saying it's a correlation of the field at some time with the field at a later time, right? I want to know how long does it stay correlated, right? So what do you think this delta nu relates to? could it relate to? I have almost given you the answer. You just have to paraphrase what I've said and give it back to. And here I was thinking long break, everyone will come to class brimming with enthusiasm and energy and be bouncing up and down to give us answers. I can't hear you, Hari. You'll have to talk louder. Exactly. So he says 1 by delta nu, this is a time. This tells you the time for which this source stays correlated. Okay? So this in fact is nothing but called the coherence time of this source. Okay? Now go back to your Michelson interferometer. Remember, you had a source, beam splitter, mirror, mirror, and then you're looking at these beams here on a detector. Right? How would you study or how would you relate this coherence time concept to be used in this interferometer? Where does time play a role in this interferometer? I said we use a Michelson to study coherence, temporal coherence. So how do I study time in this interferometer? Exactly. So I'm going to study time by saying let one beam travel one distance, let another beam travel another distance. It takes a different path. That means it's traveled over a different time, right? And then I'm looking at the interference, right? So I can always relate this coherence time to a coherence length. Okay, what will that relationship be? It's going to be nothing but the velocity with which the light is traveling, and in this case we assume it's air. It could be some other medium, but if we say it's air, and let's say we say coherence time is Tc, then I will say the coherence time is nothing but Ctc. And in the case of the interferometer, that tells me if the path length difference between these two arms exceeds the path length difference associated with this length, I will not see interference. Does that make sense? Even if I say this is a coherent source, again, I'm stressing on the point I said right at the beginning. That does not mean I can take a laser beam, split it into two beams, and then let those beams travel any different path length and say, oh, there are two laser beams, they came from the same source. If I overlay one over the other, I'll see interference. Only if certain conditions are met will you see interference. And specifically, only if the path length difference between those beams is less than the coherence length of that source will you see interference. Okay? So, now let me erase this so that you can see this. Okay. So, if you look at the numbers for this particular source, we already said 1 over delta nu is the coherence time, and if your delta nu is 1.5 gigahertz, that means 1 over delta nu is in the order of 10 to the power minus 9 seconds. That's the coherence time. Now, just because light happens to travel really fast, it means that you get coherent lengths which are still practical, right? Because you're not saying that it's 1 second, in a time of 1 second they are correlated. You're saying in a time of 0.666666 to the 10 to the power minus 9 seconds, they stay correlated. but light can travel quite a good distance in that time, okay? And that allows interferometers to become useful to us, okay? What happens after this time, after this 0.6 into 10 power minus 9 seconds? That source now starts emitting at a different lambda. What lambda? It's not emitting at 400 nanometers, not emitting at 1000 nanometers. It's emitting at some value of lambda which will lie plus minus this value by 2 off from 632 nanometers. So, I will still say, oh, this source is emitting 632.8 nanometers, but really it's emitting any wavelength plus minus this delta lambda by 2 from 632 nanometers, okay. That means the wavelength is changing, and every time the wavelength change, I have one particular wavelength. I've drawn only one wavelength, but if I had a sinusoidal wave with this wavelength, I could draw this out to infinity, it would never change. The point is that after this 10 power minus 9 seconds, there's a slight change in wavelength, which means the phase relationship is now no longer predictable, or rather it's only predictable with this accuracy, okay. Any questions? No? Okay. So, the implications of coherence is, if I were to take two different lasers, why don't I ever do interference with two different lasers? I would have to keep their phase relationship so accurate, because each laser individually you saw what's happening. If I took two different lasers and I wanted to ensure they were phase correlated, the kind of accuracy I would need is till date not achievable, okay. And therefore, you always do interference by taking a single laser source and splitting it, and even there you have some constraints on when you will see interference, okay, depending on the bandwidth, the spectral bandwidth of your source, and of course the size of your source. But in most of the applications that we will look at, we will be talking about lasers, and so we will assume then that the source has very good spatial coherence, and the temporal coherence is limited by the bandwidth, okay. Okay. So, just to put down some of those equations again, we talked about the temporal coherence and how you can relate that to the coherence length. So, temporal coherence is nothing but that 1 over delta nu. So, that is this relationship. We relate it to a length. So, how much does light travel in that time? And if we take two beams and take the interference of those two beams, and we'll do that derivation now, you will get an interference equation of this kind here. So, this is equation where you have interfered two beams, and we'll see what each of these parameters mean. One thing I haven't mentioned, but you need to take into account, I have just been talking about correlating an electric field at one point of space and time to an electric field at another point of space and time. But what needs to be taken into account is the polarization of these two beams need to be identical, okay. So, what is polarization? It is the orientation of the electric field, okay. So, if I took one source, okay, and I split it, and let's say I split it with a polarizing beam splitter. So, it's not just a beam splitter that splits amplitude, but it takes the polarization of that beam and splits it into, so I can always write polarization as a sum of, say, horizontal polarization and vertical polarization. So, let's say I have oriented my source in such a way that both these polarizations are incident on this beam splitter, and then I send one, say the horizontal in this direction and the vertical in this direction, okay. And now I interfere these. I have mirrors to redirect these. This is not a Michelson, this is a different kind of setup, and there's an interference here. I'll not see anything. The same source, the path length difference is 0, perfectly matched, but the polarizations are orthogonal. In order for two beams to interact with each other, the electric fields must either have the same polarization or there must be some overlap between the two polarization states. Okay? So, the assumption that I am going to make throughout the rest of this course is we are dealing with beams that have the same polarization. Okay? You can have interesting applications where something changes polarization partly and you use interference to measure that. Okay? So, I am not saying that we never worry about you worry about polarization, but in this course we will assume that we have beams of the same polarization that are interfering. Okay. So, the last part of this class, then let's just look at how we get this interference equation. So, I can write out the electric field. We are always going to use the electric field. Okay? So, I am going to write out the electric field for one wave. So, these are the two waves that are generated from one source. So, this is the electric field of one wave. This is its amplitude. They're from the same source. So, the omega and k in terms of the lambdas is going to be same, right, because it's same frequency. This is the phase of this beam determined by the path it has travelled. This is the phase of the second beam determined by the path that it has travelled. Now, when I say path, that means we are taking into account the distance it has travelled as well as the same question that I ask you again and again in every topic, the distance as well as the, is distance the only thing that matters? The refractive index. So, I could have I could split these two beams and one beam could be travelling through water and one beam could be travelling through air. One beam could be travelling through a medium whose refractive index I want to find out, and another beam is travelling through air. Okay? And generally in an interferometer you will refer to one beam as a reference. It's there to cause the interference, and the other beam is somehow going to acquire the information. So, it's maybe reflecting off a sample, it's passing through a sample, or its path is seeing a pressure change, its path is seeing a temperature change. That one path sees the change that you want to measure. Okay? So, usually we will say you have a reference beam and an object beam, because one beam we consider as an object, it contains information. Okay? So, I have my two beams here, they each have different phases and different amplitudes depending on how they have been split, and maybe one has reflected off a sample and that may have very much weaker amplitude. The interference is nothing but taking the sum of these fields and squaring this to get the intensity. Excuse me. So, if I do that, I am going to end up with this relationship where I1 is nothing but E1 squared, I2 is nothing but E2 squared, and this cos term is the E1 E2 dot product, right, between, because these are vector fields. Okay. So, the term of interest to me is this cosine term, because this delta is what contains the phase difference between these two waves, and that is how I am going to extract information. Okay. So, is this expression clear to you? Okay. What are the assumptions we have made here? We have assumed that E1 and E2 have the same polarization, these two fields. Okay. And we have also assumed that there is perfect spatial coherence. We are only using the temporal coherence of this source in order to, and we'll see how, where you might ask, where does temporal coherence come explicitly in this, and we'll look at that. Okay. So I think, yeah. So I'll end today's class with this. So in today's class, we've started on a new topic on interference. It's a wave phenomenon, and we looked very briefly at the most important condition that allows us to observe coherence, to observe interference, and that is coherence. Okay? So we looked at spatial coherence, temporal coherence, and we looked at the interferometers that allow us to study these types of coherence. And we've ended now with an expression for two-beam interference, and we see that it contains three terms. The first term is nothing but the intensity of one of the interfering beams. The second term is nothing but the intensity of the second interfering beam. By themselves, they give us no special information, but the third term contains or is a function of the phase difference between these two beams, and we are going to see in further classes how we can use that to extract useful information. Okay? So we meet tomorrow.